Alright, SL 1.9. I've been looking forward to go over this subtopic. This is a binomial theorem. It is one of my favorite topics in topic 1, and we need to spend quite a lot of time on this topic, especially if you're unfamiliar with it. And even if you are familiar with it, it still requires a bit of time to fully get the hang of it. So let's go over it. So the things that we'll be going over in this subtopic is the binomial theorem, binomial expansion, and also Pascal's triangle and NCR combinations and whatever it all means. So first things first, we need to understand what binomials are. A binomial is just a fancy way of saying two terms, bi meaning two being added together or subtracted from each other. This is a binomial. And what binomial expansion is all about is if we raise this binomial to a power, let's say n, and we want to expand it into many singular terms, which will help us with, for example, calculus or any other real-life applications, which I don't know what kind of real-life applications they are, but like IB, that's an application. The most common binomial that we are probably already familiar with is a quadratic. This is a quadratic. So if we want to expand this, for example, we can always take the first term squared, 1 squared plus 2ab, 2 times 1 times x, 2x, plus our last term, our second term squared, and good job, we've just expanded a binomial. So what's so difficult about binomial expansion? Well, what if I said I gave you this expression right here? The same thing, but raised to the power of 3. You could still theoretically expand it, it would just take a little bit longer. But what if I raised it to the power of 7? You can either do it by hand and write out every single term and taking decades until you get your final answer, or you can use the binomial theorem and expand this expression right here in a much faster manner. But before we get started, we need to understand what the Pascal's triangle is. This is the Pascal's triangle. Now, let's explain what everything means. What everything means on the left-hand side, this is basically our power of the binomial which we raise it to. So say we are given a plus b to the power of n. When n equals 0, we look at this first row right here. When n equals 1, we look at the second row right here, and we continue on. So looking at the first layer, when n equals 0, there's a 1. When it's n equals 1, there are 2 terms. There's a 1 and 1. And it breaks down into 1, 2, 1, 1, 3, 3, 1, etc. So where do these numbers come to be? How we write the next number is we basically look at the parent numbers above. So the parent number of this one right here is 1, because there's only a 1 above it. And 1 plus 0 equals 1. And with this 2 right here, it has 2 parent numbers. So it has 1 and 1, so 1 plus 1 is 2. In this case, 1 plus 2 will make 3. Let's say 6 plus 4 is 10. 5 plus 10 is 15. And you get the next number by looking at the 2 numbers above it. So it's a pretty simple set of numbers to derive. And all you need to start with is just this little triangle of 3 ones, and then you can work your way from there. And notice that they are only going to be 1s on the left and right edges of this triangle, because 1 plus 0 is always going to be 1. So what do these numbers actually mean? Well, take this quadratic for example. This quadratic is 1 plus x to the power of 2, right? If it's 1 plus x to the power of 2, that means n is equal to 2. Our power is equal to 2. And we refer to this row right here. And notice 1, 2, 1. The coefficients are 1, 2, and 1. Now, this actually may not always be the case, but because this example is so simple, it actually works. But the numbers in this triangle right here is basically how we're going to be expanding binomials really quickly. And one last thing before we move on is this term right here called NCR. Now the C actually refers to combinations, and combinations and permutations is actually a HL topic, but in SL, all you need to know is that NCR basically just means the N meaning the layer, and R meaning the term. Say we wanted to find 4C2. It's basically asking us to find the second term on the fourth layer, on n equals 4. So if we look at n equals 4, we go 1, 2, This is actually not what we want to find. We want to find the third term of the third layer, because what we need to note is that all of these numbers here on the left-hand side, this is actually n equals 0. Otherwise, we wouldn't be able to find what this number is, because this number right here is 0C0. Now, you can actually do this on a calculator. I'll be using the Casio FX-82AU Plus 2nd Edition Scientific Calculator, but it also works on other calculators if you can just find the NCR button. And how you want to input this is, for example, you want to find the fifth number on the 8th row, on n equals 8. All you need to input is 8, and then you find your NCR number. In this case, it's on the divide sign, so I go shift divide to get the C, 8C5, and then the number on the left will be our n term, the number on the right will be 5, and we press enter and we get 56. Now, I know this is very theoretical and you might be wondering why we need to know all of this, and I'll show you right now. So here is our equation of the binomial theorem. Even though this is a very long equation, it's actually very simple. Let's write out our binomial again for a plus b to the power of n. It's also written right here, where n is a natural number, meaning it is a number, an integer greater or equal to 0. Now, let's just start with the quadratic that we had in our last slide and see if it actually works. And in this case, let's identify our a term. Our a term will be 1, our b term will be x, and our n will be 2. Okay, so this is our variables, and let's use this equation. We want to start by a to the power of n. 1 is our a, so 1 to the power of n, 1 to the power of 2, plus n brackets n on 1. So n is 2 and 1. Now, I'll explain what this actually means in a second, but let's continue. Multiplied by 1, which is a, to the power of n minus 1, which is 2 minus 1, multiplied by b, which is x. And how this series continues is our r term, which is going to be this number right here, it's going to increase continuously until it becomes the same number as n. And when it becomes the same number as n, then we'll reach this last term right here. So in this case, it will become 2 on 2. And this is actually already our last term, but we'll just use this to show you why it is the last term. And multiplied by 1 to the power of 2 minus 2, multiplied by b, which is x, to the power of 2. And if we simplify everything, we'll find that 1 squared is 1, plus 2 on 1 in the brackets. This is actually the same thing, if you refer to this equation right here, as just 2c1. And we know from the Pascal's triangle, the first number on the second layer, n equals 2, this is r equals 0, and this is r equals 1, will just be 2. So 2c1 is equal to 2. Hence, 2 multiplied by 1 to the power of any number is 1, multiplied by x, and we're going to add 2 on 2, 2c2. Again, if we look at Pascal's triangle, the second number on this layer will be a 1. And this means that we've reached our last term, because we can actually identify how many terms there are within a binomial by just adding 1 to n. If it's a quadratic, if we have 1 plus x squared, there will be 3 terms, because on n equals 2, there are 3 r values. So this is our last term, and 2c2 is actually just 1. Multiplied by 1 to the power of any number is still 1, multiplied by x squared, which will just give us x squared. Hence, we could have very well just plugged in this last term, b to the power of n, right? Because b is x and n is 2, so it could have just been this plus bn, or x squared. But I just wanted to show you how the equation is used. But once you get more familiar with it, you'll realize that when your r gets to the same number as your n, that is going to be your last term. And now if we look at this quadratic, this is actually the same as our quadratic which we expanded much earlier in the video. So the binomial theorem works. And it seems like we took a much more complicated route than we should have. Instead, we could have just expanded it straight away, but we had to go through all the trouble of this equation right here. But it is, as I said, a lot more helpful when you're given larger coefficients, which we will get to later in the video. And just before that, another thing I want to go over is this over here. I actually didn't talk about this equation. This is the third method for how you can find NCR. So we've already established our first two methods. One is using Pascal's triangle, being n meaning the layer, and r meaning the term, starting from r equals 0, r equals 1, r equals 2, etc. That would work for small numbers because you can actually just work out the first couple layers of the triangle by just looking at the numbers yourself. Or if you have a calculator and then type in NCR. Or the third method for when you don't have access to a calculator and the numbers are too big for Pascal's triangle is you can always opt for this. And all you need to do is just sub in the relevant numbers. So if you want to find the fourth term of the fifth layer, for example, you want to find 5c4, you can just plug in everything and just get 5 factorial on top of 4 factorial multiplied by 5 minus 4 factorial. Now, what factorial actually means, let me just rub out some of this over here. If we're given 5 factorial, we want to find 5 multiplied by every single integer less than it, right? It's just going to be 5 multiplied by 4, multiplied by 3, multiplied by 2, multiplied by 1, until it gets to 1. So you're going to be minusing your number by 1, and you're going to multiply that, and you're going to keep doing it until you reach 1. And you don't actually need to expand everything to figure it out. If you don't have a calculator, this is still going to be pretty hard to figure out. But what you can do is you can realize 5 factorial is the same thing as 5 multiplied by 4 factorial, because 4 factorial is just 4 times 3 times 2 times 1, right? So 5 factorial is just the same as this. On top of 4 factorial multiplied by 5 minus 4, which is just 1 factorial. And the 4 factorials cancel out. So you're left with 5 on top of 1. 1 factorial is 1, and that's 5. So you can also figure out NCR relatively easily by just using this equation right here. Okay, now moving on to some practice questions. Expand 2 plus x all to the power 4 and simplify your result. Now this is an example of a binomial which takes much less time if you know how to expand it efficiently using the binomial theorem than if you were to expand it manually. So let's give it a try. Let's first identify the different terms within the binomial. Let's make a equal 2, b equals x, and n will equal 4. And now let's substitute everything and see what we get. A to the power of n, 2 to the power of 4, plus nc1, n is 4, so 4c1, multiplied by a to the power of n minus 1, which will be 2 to the power of 4 minus 1, multiplied by b, multiplied by x, and we continue. Now we raise r by 1, so we get 4c2 multiplied by 2 to the power of 4 minus 2. So our r here, 4 minus r, it will increase from 1 to 2, and x to the power of r will be x squared. And we continue. 4c3 multiplied by 4 minus 3 multiplied by x to the power of 3. Now I was able to do that very quickly because all I needed to do was just replace this 2 here. This is the r, this is the r, and this is the r. I just needed to replace all 3 of those variables with 3. And for the fourth term, we can either write out 4 for all the r terms, or we can realize we've reached the last term and we can just write x to the power of 4. Once again, if we substituted 4 for r, we'll get 4c4, which is 1, and 2 to the power of 4 minus 4, which is still 1, giving us the same thing anyways. And now, let's simplify. 2 to the power of 4 will give us 16, plus 4c1. Now, once you get more familiar with the Pascal's triangle, you will actually start remembering the rows. But when you first start, it's fine. You can always draw out the triangle, or use your calculator, or even use this equation right here. But I'm just going to let you know that for n equals 4, the row is just going to be equal to 1, 4, 6, 4, 1. And therefore, 4c1, which is this term right here, will just be 4, multiplied by 2 to the power of 3, which is 8, multiplied by x, plus 4c2, right here, it's 6, multiplied by 2 squared is 4, multiplied by x squared, plus 4cu3, which is 4, multiplied by 2, because 2 to the power of 1 is 2, multiplied by x cubed plus x to the power of 4. And once again, let's simplify everything. We'll get 16 plus 32x plus 24x squared plus 8x cubed plus x to the power of 4. And this right here is the expansion of 2 plus x all to the power of 4, and it is the answer to part A. Part B, we want to find the term in x squared in this expression right here. Now, if we notice, we've actually already finished our expansion of this first part over here, and we are only left with here. So what it's asking for is after we expand everything here and simplify, we'll be left with a series of terms, like a constant term plus something x plus something x squared, blah, 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 blah. And what we're interested in is the question is asking us to find this term right here, the x squared term. So the smart thing to do here would not be writing out the entire expression that we found in part A, like this, and multiplying everything term by term in order to get our x squared term. Because then you would be multiplying every one of these numbers by 1 and every one of these numbers by 1 on x squared. And you'll end up getting 10 terms, which will not be necessary because you're just going to be wasting your time. And especially under exam conditions, that's probably not ideal. Instead, what we want to recognize is that some of the terms multiplying will not actually give us the answer. We only need to recognize the terms which will multiply to x squared. So for example, what I mean is, if we multiply 16 by 1, that is part of the whole expansion, but 16 multiplied by 1 is 16, and that doesn't actually help us get the answer for this question specifically. So we can just ignore that. Same with 32x multiplied by 1. That will not give us an x squared term. So we need to find a number out of these 5, which multiplied by 1 will give us an x squared, and we'll need to add that to the product of one of these terms with the second term in this binomial right here. So let's start with the 1 over here right now. What number out of these 5 multiplied by 1 will give us an x squared term? Well, obviously it would be the 24x squared, because 24x squared multiplied by 1 will just give us 24x squared. And now for our second expansion, right here, 1 on x squared, we can actually rewrite this into x to the power of negative 2 to make it a little bit easier. What number out of these 5 terms right here multiplied by x to the power of negative 2 will give us an x squared term? Well, if we think about our indice laws, when we are multiplying two terms together, their powers will add. So what number plus negative 2 will give us 2? Well, if we just do our algebra, or think about it logically, it would have to be 4. So we can multiply this x to the power of 4 term. So we can multiply this x to the power of 4 term by our x to the power of negative 2. X to the power of 4 multiplied by x to the power of negative 2. When we're multiplying two numbers of the same base, the powers will add, and we'll end up with x to the power of 2. So our second term here will be x squared. Now, even though if we expand everything fully, we'll have a lot of terms in front and a lot of terms after as well, the other terms are irrelevant because they will not be x squared. They might be just a constant term or some coefficient multiplied by x, some coefficient multiplied by x cubed, etc. But these are the only two terms that will contribute to the term of x squared. And therefore, the answer to part B is equal to 25x squared. Okay, now moving on to the next question, we have this right here. So if we read this question, we can see that we are given two binomials, this one right here and this one right here, and these together, they will multiply to form a product which is equal to this expression right here. And we want to find the value of n. Now there are two tricky parts to this question. One being the binomial here is to the power of n, meaning if we want to use NCR, we will not know what n is, and it might make things a little bit more complicated. And another thing is that on the right hand side, we aren't actually given the full expression, and we're only given up to the x term. So we need to find a way to work with that as well. So first things first, we will not be able to expand this term fully because we don't know what the value of n is. Therefore, we have to look at what the terms correspond to. And what I mean by that is when this binomial here is expanded, we're going to have a constant term, a x term, an x squared term, x to the power 3 term, and potentially it keeps on going after that. And depending on what n is equal to, we'll have however many terms. So therefore, if we were to expand the first binomial, we'll get something like this. And if we expand the second binomial, well, we can actually just do that by hand really quickly right now. We don't actually even need to use the binomial theorem because it's only a quadratic, so we can just take a squared plus 2ab, which is 2 times 3 times nx, which is 6nx, and then plus n squared x squared, the square of our b term. And this is our expression, right? This is the same thing as this. And now what we must realize is we don't actually need to know the x cubed term or x to the power 4 or x to the power 5 terms, if there are any, because they are insignificant to what we are given right here. We aren't even given the x squared and x cubed terms. So if we were to expand the product right here, say we multiply 9 by x cubed, that doesn't actually help us solve the question. So all we need to know is the first couple of terms. And in fact, we only need to know up to the x term. Okay, we don't even need to know the x squared term. Because if we think about it, if we multiply our constant term of our first binomial by our 6nx, our x term of our second binomial, we are going to get our x term. And this goes the same for if we multiply our x term of our first binomial by our constant term of our second binomial. And this way we'll be able to calculate what the x term is equal to in terms of x. And we can compare it to 84x in order to work out what n is. And just a quick note on why we only care about this term right here instead of the 9 as well, is because I actually know that we will get a 9 either way, and this is the term that will help us find n. Why is that? Well, because if we think about it this way, if we were to expand this, we have to start with a to the power of n, right? And a to the power of n, in this case, a is 1, and 1 to the power of any number will still be 1, meaning our constant term will be 1 on the left binomial. And on our right binomial, it will be 9 because it will be 3 squared, right? So the two constant terms will just be equal to 9. And what we're given in this expression is also equal to 9. So we've basically just proven that 9 equals 9. But that actually doesn't help us find n, because the only way for n to show up in our equation is if we move on to the r equals 1 term where we have nc1. So we want to now expand our binomial to the x term. And we can use this equation right here until we reach the x term. Let's actually start by identifying what our variables are. So a will be 1, b will be 2 on 3x, and n is obviously just n because we don't know what that is yet. And now if we substitute everything in, let's see what we get. The first term will be a to the power of n. It will be 1 to the power of n. Now our second term will be n on 1. Okay? And we don't know what n is, so it'll just be nc1, a to the power of n minus 1, which is just 1 to the power of n minus 1. And we know that 1 to the power of any number is just equal to 1, but I'll write it out here just in case. And it's going to be multiplied by our b term, and that will be 2 on 3x. We'll actually stop here because if we continue, our r will become 2. That r basically just means the term number. And if our r is 2, then we'll get b squared. And b squared will mean our x will become an x squared. And we don't want that because we've already established we only need up till the x term within our first binomial. So in reality, we've actually already finished expanding our first binomial. And now all that's left is that we have to simplify this. So 1 to the power of any number is 1 plus nc1. And if we think about it in terms of a Pascal's triangle, let's just draw it out right here. nc1 is actually equal to n. And this is because, let's say we are given n equals 2. This is the second layer. And this is r equals 0. This is r equals 1. For any layer, when r is 1, our term will just be the same thing as our layer number. So in this case, if we want to find, let's say, 4c1, we have the fourth layer. What is the first number in the fourth layer? Well, it's going to be 4. So in this case, NC1 will just be equal to n. And again, 1 to any number is 1. So we are left with 2 on 3 nx. And this is our first binomial expanded. Okay, and now for our second binomial, we already know, we previously expanded it. It will just be equal to this right here. And we know this entire thing is equal to this expression right here. In reality, we do not need our second term right here because it consists of an x squared, and x squared will not be useful for us, so we can just ignore that. So we will have 4 terms only in total, and let's multiply them out one by one. 1 multiplied by 9 is 1, 1 multiplied by 6nx is 6nx, 2 on 3 nx multiplied by 9 will give us 18 on 3 nx, and 18 on 3 can just be simplified into 6. And our last term here will be 2 on 3 nx multiplied by 6 nx, and I actually don't need to write this out because it will equal to an x squared term because the x's multiply. And again, we do not need the x squared term, so we can just ignore that for now. And now we are only left with 3 terms. And these 3 terms should be equal to 9 plus 84x. The 9's cancel out. On the left side, we are left with 12nx equals 84x. Divide by 12 on both sides, nx equals 7x. And cancel the x's, we are left with n equals 7. And right there is our answer. N equals 7 to a 7-mark question. Okay, let's do another practice question. Let's consider the expansion of this expression right here. And we are given the constant term equaling to this, and we want to find k. And this is actually a 7-mark question, so it is also pretty difficult. But that means if you understand this question, you are on the right track to understanding binomial expansion. First things first, what we want to note is this idea of constant term right here. Constant term just refers to the term without an x. Right? It is our first term right here. As you can see, there is actually an x, but it just be x0. And this is the value right here. So what we want to do is we want to expand this right here via binomial expansion. Now, expanding this whole thing would be a waste of time because you end up getting many, many terms. So the best thing that we want to do is we want to identify for what number of r, meaning our term number, in this case, for example, this is r equals 1, this is r equals r equals 0, this is r equals n, right? So for what number of r, or which r term, will allow us to get a constant term? Because if we expand a binomial, let's say we expand a binomial like this, a quadratic, we have r equals 0, being this, we have r equals 1, and we have r equals 2. So each one of these terms actually all correspond to an r term, being 0, 1, and 2. And we want to find which r term will allow us to get a constant term. Because if we are able to identify that, all we need to do is just use this one general formula instead of using the whole thing, and by substituting our r value in order to find the singular term that we need, which corresponds to the constant term that we are given in the question. Okay, hopefully that made sense. So how do we identify the constant term? So what I like to do is I first like to note that this is actually not part of the binomial, and it will stay x squared forever. And I like to work from the back. Instead of expanding this straight away, I want to realize that no matter what we get out of this expansion right here, we're going to have to multiply it by x squared. Therefore, the term that we are looking for in this binomial expansion is actually the x to the negative 2 term. Because once we get that term with a coefficient and we multiply it by the x squared term at the front, we'll end up with an x0 term or a constant term. So in reality, what we are looking for in this expansion, in this binomial expansion right here, is not actually the constant term, but rather the x to the negative 2 term. Let's identify our 3 terms first. Our a term will be 3x squared, b term will be k on x, and for the sake of it, I'm going to write kx to the negative 1, that's the same thing, and our n will be 8. And now if we copy out this general formula here for one of our terms in our binomial expansion, it will simply be 8 on r multiplied by a, which is 3x squared, Notice you have to put the brackets around the whole term, to the power of n minus r, which is 8 minus r, and b, which is kx to the negative 1 multiplied by r. And this right here, what we are looking for is that it will equal to 16128x0, or just plainly 16128. Now, first up, there are some things that we can just ignore, because right now we have too many unknowns. We have k unknown, we have x unknown, but the x's actually will cancel out. But we have r and k unknown, and that is not actually solvable at the moment. So what we need to do is we need to identify what r is first, and then we go back to solving for k. So what we are looking for is a value for r for which the x terms will cancel out, hence the constant term right here. Therefore, looking at this expression right here, we can just ignore this, because any number on the Pascal's triangle, on the 8th line of the Pascal's triangle, will just be a number. It's not going to have a variable in it, or it's not going to have an x in it. So we don't actually need to think about this. This 3, again, we don't need to think about it at the moment, and this k, we don't need to think about it. All we need to think about is just the x's. So we can actually rewrite this line as just the indices. If we think about it just in terms of the indices outside here, the power of outside the brackets, will multiply by the power inside the bracket. So what we'll get is we actually get this. X to the power of 2 times 8 minus r multiplied by x to the negative r. And this will have to equal x to the power of negative 2. And the reason why this doesn't equal the constant term is because when we identify the x equals negative 2 term again, it will cancel with the x squared over here, giving us the constant term overall. And now what we can do is we can use our indice properties of multiplying two indices of the same base, meaning the two indices will add. So we can simplify the left-hand side to this right here, and we're going to have to add it to negative r, or in other words, just minus r. And then it will equal to the same thing over here. And now if we think about it logically, x to the power of blah 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 will equal x to the power of negative 2. And since it has the same base, we can literally just ignore the x's and just only have an equation for the indices. Because if the indices are the same, that means our left-hand side will be equal to the right-hand side, given it's the same base, and there's nothing else going on in the equation. So I've just rewritten the equation right here, and let's simplify it a little bit, and we'll get something like this. And we'll simplify it one step further. Let's just bring it up here. We'll get 16 minus 3r equals negative 2. And here, let's add 2 to both sides. We'll get 18 minus 3r equals 0. Add 3r to both sides. 18 equals 3r. Divide by 3, and we'll find that our r is equal to 6. Now, that is not our answer, but what this r value represents is that the term for when r is equal to 6, when we expand this binomial right here, will be some number, some coefficient, followed by x to the power of negative 2. And when we multiply that by x squared, we will end up with a constant term, x0. And in this case, we can compare the left-hand side to the right-hand side that we are given, and we can find k that way. So now that we know r is 6, let's identify the term for when r is 6 in our binomial expansion. So now let's use our general equation right here to find what our binomial expansion will lead to for when we substitute r equals to 6. So the first thing here is n on r, so NCR. N is 8, r is 6, multiplied by a is 3x squared to the power of n minus r, which is 8 minus 6, multiplied by b, which is going to be kx to the power of negative 1, and we're going to raise that to the power of r, which is to the power of 6. And this right here will be our x to the negative 2 term. And when we multiply it by x squared, which is given in the question right here, we will end up with 16128. And this is the final equation that we need to solve for this question. So now all we need to do is just simplify and find out what our k is equal to. Even though there are two unknowns right now in the question, hopefully we found the right r value for which all the x's will cancel out and we'll only be left with one unknown. In this case, it will be k. So this is a paper 2 question, so we can use the calculator to find that 8c6 is equal to 28. And we want to multiply it by this right here, so 3x squared to the power of 2. We will get 9x to the power of 4. And for this time right here, we can use the distributive property again, and we will find that it will be equal to k to the power of 6 multiplied by x to the power of negative 6, because the powers distribute to both terms. And this will be equal to 16128. Now let's group the x terms first. We find that everything in here is just composed of multiplications, so the brackets actually don't matter and we can multiply in any order. And what we'll find is we're actually left with, let's just write out everything at the front here that we will need to keep, and our x terms. So here we're left with x squared, and here we have x to the power of 4, and here we have x to the power of negative 6. And what we realize is that when multiplying indices of the same base, the powers will add. 2 plus 4 plus negative 6 will just be equal to 0, giving us x to the 0 or 1. So we've actually done it, and we have actually gotten the constant term. So this whole thing just cancels out. Now we can just simplify a bit further. 28 times 9 is 252, multiplied by k to the power of 6 is equal to 16128. Now if we divide both sides by 252, we'll find that k to the power of 6 is equal to 64. And if we take the sixth root of both sides, let's just bring it up here again, we'll find that k is equal to 2. Or, in reality, it should be equal to plus or minus 2. And that is because when we raise a negative number to an even power, it will still become positive. If we raise negative 2 to the power of 2, it will become positive 4. And if it's odd, it will be negative. So in this case, because it's an even indice right here, an even power, the answer is actually equal to two numbers being plus or minus 2.